go ahead and get started. Okay. All right, so last time we left off, molar mass. You will notice that it looks much like what we were talking about in terms of atomic mass. Remember that? Okay. So chemists have played a trick. Did you notice Avogadro's number was some weird number, right? It wasn't like a 10 to the period. It was 6.02 times 10 to the 23rd. Very strange number, right? The reason that was made as it was is because, hey guys, you need to not try to talk over me. This is not going to work out. Okay. The reason that was made as it was is because it was done so that this number, 22.99, represents two things. It represents the atomic mass average of sodium that you'd get from nature. Okay? That's true. It's a number in AMU. But it's also a number that's in what's called grams per mole. It's how many grams a mole of sodiums from nature would weigh. Okay? Isn't that cool? They managed to get it the same numbers for all these different units. Smart, right? Yeah. Made it so everything was much more uniform on the periodic table. Imagine if they'd screwed that up. You would have had two numbers like these on the periodic table. Completely different, right? Yeah. Okay. And so this number is how many grams a mole of a substance would be. This is referred to as molar mass. That is grams per mole. And so right here, if we have a mole of carbon, how much would that weigh? 12.0 grams, right? 12.01 grams. And so again, that same atomic mass is the same number for the molar mass. The only difference between those is the units. Atomic mass is in AMU. The units for molar mass is grams per mole. Okay? All right, so the molar mass from your periodic table, if we were to go ahead and look at carbon, this is carbon right here. Notice we weighed out a mole, and so it's 12.01. We know that's a mole, right? All right. Notice how much a mole is. Kind of a moderate amount of substance, isn't it? Yeah. Yeah. It's something that's easily weighed and measured in a lab. Okay? That was the idea behind moles and why we did moles. Okay? All right, so this is actually 1 mole of different substances. Here we have sulfur, iron, NaCl, potassium chromate, and right there, anybody know what that is? Any ideas? That's sugar. That's sugar. I know. That's the formula, what sugar's formula looks like. There's actually a few different types of sugars, of course. But they all look something like that. All right, so let's go ahead and practice using these. We're going to calculate the molar mass for lithium carbonate, and that's lithium carbonate's formula right there. This is actually used to treat bipolar disorders, very common medication for that. You guys may have seen this around before, or maybe not. And so how are we going to calculate the molar mass for that lithium carbonate? So could we look up at lithium and just take lithium?
No, you have to get all of them.
We have to get all of them. And how do we know how much of each there is? Yeah, we take the number on the periodic table, we multiply it by the number in the formula right here, right? So there's 2 of the lithiums from the periodic table, there's 1 of the carbons from the periodic table, there's 3 of the oxygens from the periodic table. We add those together. Mm-hmm.
So it has to be on the bottom. Why is that again?
What do you mean?
Why is 1 on the bottom? The 1 mole.
Oh, this is because that's the definition of molar mass. It's the number of grams for 1 mole of a substance.
Okay.
And so those are the units of molar mass, which is what we're trying to get out of this. Yeah.
Okay.
And so that's the number from the periodic table right there. In this case, we're using grams per mole because, again, we're looking at molar masses. Okay? and that's the unit for molar mass. And so we multiply that number by 2 here, because that's the number of lithiums in the formula. Everybody say okay? There's 2 lithiums, so we multiply by 2. Carbon only has 1 of them, so it's times 1. And then oxygen has 3 times 3. Okay, that making sense? Am I losing anybody? Okay, fantastic. All right. Okay. Now, when we do that multiplication, what we're going to see is that if you have 2 moles of lithium, we're going to have 13.88 grams of it, and so on. Now, to get the entire formula, we actually have to add all of these together, don't we? Yeah. So we go ahead and add all these together, plus, and that gives us that right there, which is 73.89 grams. Okay. Fantastic. In case you need to join, there's the join for the Q&A. Okay. All right. And it will pop up in a bit again if you can't get it, plus the number you can also use to access things. All right, so let's calculate the molar mass of C2H6O. This is going to actually be another example where I'm going to show you again how to do this bit. So what are we going to do? Yeah, we're going to start with carbon. We look the carbon up on the periodic table, right? And we multiply by what? 2, exactly. And then we look up hydrogen, and we multiply that by 6. We look up oxygen, we multiply that by 1. And then we do what? Add them all up. You got it. Sum it up. Okay. Is anybody getting confused by this at all? You are? Okay. Okay. So again, we just look at the periodic table numbers. That's all these are going to be. Okay? Those numbers have a duality. They can be grams per mole if we want them to be grams per mole, or they can be AMU. Okay? In this case, we want grams per mole because it asks for molar mass. Okay. So these are just the numbers from the periodic table right here. All put in 4 sig figs. Okay, and so we take those numbers, we multiply them by the number of times they show up in our formula here. That's these. Okay. And then we're going to just add these together.
I remember. It took a moment. I got it.
Okay. Fair enough. Okay, so let's talk about molar masses as conversion factors. You may have noticed that the molar masses were relating grams and moles together, aren't they? Okay, so if I have moles of something, then I can use the molar mass to get grams, can I? If I have grams of something, I can use the molar mass to get moles. And so they are also conversion factors. We can write them as those conversion factor ratios. We can also write them as equalities. Okay? Okay. The same as we did every other conversion factor before this. That also works. So a box of table salt that contains 737 grams of sodium chloride. How many moles of sodium chloride are present in that box? So how are we going to go about this? We have grams of something. How do we get it into moles then? Yeah, we're going to have to get the molar mass of an ACl, right?
Yeah.
And then
divide 737 by that.
you got it. And divide that grams by the grams per mole molar mass.
So divide by 57 and change.
So,
Exactly, yeah.
so if we're converting them mass to moles, I'm kind of confused with this part. I'm not really catching on.
Okay.
So a box of salt contains.
So we have a grams number.
Yeah.
We want it to be in moles.
Yeah, we'll put that one on top, and then.
Okay, so we're going to take the grams number. Okay. Let's first go ahead and get the molar mass, because we're going to need that. It's always better to work in concrete terms. NaCl, exactly. So we'll look up Na from the periodic table. and Cl from the periodic table. There's one of each in this case. By the way, correctly stated, this would be called a formula weight. It is not actually a molar mass, correctly stated. But doesn't matter. If you want more of that stuff, we can talk in a higher level chemistry if you ever want to take that. Okay. Now,
So if we were writing this in a formula way, without using any specific elements, would it just be grams, then would it, like, what would it be if you wrote it as like an actual equation? Grams, would it be multiplied plus?
be grams,
Uh-huh.
and then you're trying to get rid of grams and go into moles.
Wait, so you'd be dividing?
You divide, yes, your grams per mole number, which is the molar mass,
Grams divided by mole number,
by the molar mass,
by molar mass.
which is grams per mole. But this is not actually something that you benefit by memorizing a formula for,
You can't just plug it in?
because you're always going to have to do these additions right here. So you got to be very careful, because you're going to be doing an addition. Okay. So let's go ahead and do the problem. It's best to just do the problem. They're not actually something new. This is just unit conversions. You've done hundreds of these before. It's just a unit conversion. Okay. The same as the first 4 chapters. Remember that?
Still plan on doing 2 decimals?
In this case, we're going to end up doing at least 3 sig figs. Okay, so we're going to go on the periodic table. We're going to get Na and Cl, right? And those are the numbers for NaCl off the periodic table. In this case, there's 1 Na, there's 1 Cl in the formula. Everybody said okay? We need to add those together. That number is actually a grams per mole number. Okay? Because we've added 2 numbers that are in grams per mole, right? Okay. Now, this is going to give us 58.44 grams per 1 mole. Okay.
Put that on top.
So we have 737 grams of NaCl. That's what we have. Remember, you always want to do, what do I have? What do I need? How do I get there? Okay. So I have 737 grams of NaCl. Okay. I want to go from grams to moles, don't I? And then I have this conversion factor, or this molar mass, that is grams per mole. So that conversion factor needs the 58.44 grams on the bottom, so grams are going to cancel. And it needs the 1 mole that was on the bottom before on the top now, so that we can go into moles. Okay. Okay, so that gives us 12.6 moles of NaCl. You'll notice again that this is not actually something new. The only new thing I added to your understanding was the concept that those numbers on the periodic table are in grams per mole. It's actually the only thing I added to it. Everything else was just stuff we've done.
So I have a question. So for like oxygen, it's like 15.9994. It would just round to 16.00.
Yes, you're going to end up rounding 16.00, but when you put things in your calculator, it's best just not to round. Round at the end.
Okay, so we just should keep that and put
Yeah.
that whole number in the calculator.
Yep, every time you do calculations, just plug in every digit you can get. Okay? Round at the end, otherwise you'll have rounding errors that build up and up and up and up.
Okay.
Okay, I'm gonna ask you a question in just a bit. So you'll want to join this, and I'll start asking the question right now as you're joining. So a sample of water has a mass of 59.8 grams. Everybody writing that down? 59.8 grams.
And
It's
is
water.
H2O, right?
It is. How many moles of water are in the sample?
2 hydrogen, 1 oxygen.
So, I'm sorry. Can you repeat that?
So water,
Okay.
we have 59.8 grams of water.
Okay.
How many moles? Okay.
Oh, wait, this is just like the other one you just did.
It is.
Oh, shoot, okay.
Yeah, I'm always doing that, right? I'm always working a problem, then giving you something that's almost exactly like it. Yeah, just different enough you can't just willy-nilly put stuff in. Okay, and so let's go ahead and go forward. Everybody ready?
Oh,
Got an answer in your head? At least a ballpark one? Okay. All right, we're going to go forward. Do your best. Go.
no, oh my gosh, I didn't do it in time. Damn it.
Okay,
I'm too slow.
we'll flip back. Go ahead.
Okay. Oh my god, I don't even know.
If you can't figure it, you can guess. It's okay.
I can't figure this out.
Yeah, that's why I gave you a bunch of time on the other screen. Yep, 3.32. You got it. 94%. Good. That's actually excellent. Okay, so how do you do this problem? Well, you're going to take the 59.8 grams, right? You're then going to take the numbers from the periodic table, add them together. So 2 plus 16, right? You're again going to take the 59.8 grams, divide it by that 18.02 grams per mole. And that's going to give you the 3.32 moles. Okay. Okay. So,
I want to write that formula down. I'm trying to figure out if there's any.
okay, it's in the slideshow, and that's the same problem that we've done. This will be the 5th time. So I gotta kind of move on. I can't. Okay, so we're gonna write a chemical equation here. When we have a reaction, let's say we're talking about making hamburgers, right? So for every hamburger, we have 1 meat patty, 1 cheese slice, and then 2 buns, right? Everybody okay with that? Comfortable?
That's the worst.
Wait, hold on.
It's kind of a boring cheeseburger, but yes. Yeah. Okay. And so when we put these things together, we get a product, right? So in this case right here, we're actually burning coal. Coal is carbon. And so we're going to burn coal in the presence of oxygen. That's burning. The carbon is going to react with the oxygen, and it will produce CO2. Okay? Okay. And so it's that same formulaic, same equations as we saw before. One of the things I want to point out is that when we write a chemical equation, yes, it's an arrow telling you you're going from reactants to products. But that arrow really means the same thing as you've always done for equations, right? It's just the same as an equal sign. It just tells you direction. Okay? And so the things on the left always have to equal the things on the right, don't they? If you were looking at equations and you had a 1x on one side and a 2x on the other, are they equal? Not yet. No. Okay, so let's write chemical equations. To write them, you need an arrow. It separates the reactants from the products. The reactants are, by definition, written on the left side. This is a old... so reactants are written on the left side. For your purposes, this will be fine. You'll never actually need to deal with anything else. Okay? For anybody that's going to deal with chemists, though, For a chemist, the difference between reactants and products is a bit nebulous. Okay? We'll flip-flop things a lot because it's an equation, right? You can flip equations freely. Okay? Okay. And so multiple reactants on products are going to be separated by plus signs. Delta sign is going to indicate that heat is used to start the reaction, and it may indicate that you need to provide heat if you see the delta in line with reactants or products. It'll mean that you either need to continuously put heat in as a reactant, or heat will come off as a product. So the physical states of compounds are going to be denoted in parentheses. S is for solid. A italic L is for liquid. It's always italic, so it doesn't look like a 1. G is then for gas. AQ is for aqueous. Does anybody know what aqueous means? Like aqua.
Like water.
Like water. Yeah. It's dissolved in water. Which is what that means, dissolved in water, aqueous. Okay, these are a summary of all of those that I just mentioned. So in a balanced chemical equation, we're going to have what's on both sides balanced. Okay? If you have 4 hydrogens on the left side, how many hydrogens need to be on the right? 4. You got it. If we have 2 oxygens on the left, we need 2 oxygens on the right. Exactly. So we cannot gain or destroy mass. We cannot gain or destroy atoms. We have to keep the same numbers on both sides. The numbers on the reactant side are going to be denoted as such. Is everybody comfortable with reading that okay? Okay. Okay, notice here this number 2 in front of the H2. Okay. One of the most common mistakes students are going to make is that they're going to try to write something like, yep. Is that the same thing as 2 H2s? No, that's totally wrong, right? That's because that's a whole different compound, isn't it? That would be like saying, 2 carbon monoxides is good, just as good as a carbon dioxide, right? Okay. If you think that's the same, then you should try breathing them. I won't actually recommend it because you would die.
So the comma around that G, that means it's gas.
It does.
Okay.
You got it. So this is a gas here. Those are all gases. Okay. All right, so let's write the equation using the correct formulas for the reactants and products. Right here we have our reactants, right? Here we have our products. Okay. It isn't balanced.
Oh, okay, you have to, okay.
Yeah.
Oh,
So how do we balance this?
and the 2 next to the AL and A3 next to this.
You got it. So in front of the AL, we need a 2. In front of the S, we need a 3. These are referred to as coefficients.
Wait, in front of it?
Yeah, in front.
Oh, okay.
Okay. Like so. Now, again, notice that coefficients, notice the terminology, what that sounds like. That's the exact same thing as when you were doing, like, algebra, right? Remember your algebra, pre-algebra class that you took way, way back in the day? Those were called coefficients as well, weren't they? So you're putting a 2 in front of x, a 3 in front of y, right? Coefficients. And we're just doing the exact same thing. In this case, our variables are just going to be compounds, aren't they? Okay, they're going to be chemical formulas. All right, so let's go ahead and try another problem here. We'll work it together. State the number of atoms of each element on the reactant side and the product side for each of the following balanced reactions. Okay, now P, how many P's are there? How many phosphoruses? 4 total, right? How about BR?
6. Well, this is 2 right there.
There is. There's 6 2's, aren't there?
Yeah.
So what is 6 2's? Sets of 2's? 12. There's 12 BRs, right? Got it. Okay, so that's the number of reactants. By the way, if you're a smart aleck, you can actually save yourself some work. It says they're balanced. If they are balanced, what does that mean? The number on the reactant side is equal to the number on the product side. So if you're a bit of a smart aleck, you could have just went, well, then we have 4 Ps, 12 BRs, right? On the product side as well. Yep. And that is true. 4 Ps, 4 times 1, and then 4 times 3 is 12, so 12 BRs, right? Okay, how about this one right here? How many ALs? 2. Got it. How many FEs? 2 again. How many oxygens? 3. Very good. Okay. Anybody having any trouble reading this?
That one's balanced.
It is, indeed. Yep. All right, so let's balance the chemical equation when solid Fe3O4 reacts with hydrogen gas, produce solid iron and water. So we're going to be making solid iron and water from reacting with the hydrogen gas. Let's go and put this together. So what's your reactant side going to look like? So what does this say? Solid F3O4 reacts with, right? Hydrogen gas. So those are going to be on our reactant side, aren't they?
Yes.
Okay. And so what's the first thing we put on reactant side?
Fe3O4 plus.
Got it. Oh,
And then
wow.
put the G in the S.
It's not all right for you.
No, it's really weird. Yep. And we need, what's the symbol for the phase?
G. You have to put G for gas, right?
So this is a solid.
Or is it S? Don't you have to put G's for you?
So we have
For the hydrogen gas, yeah.
Okay. Well then on the, okay, yeah, on the.
Okay. Now, always leave a little bit of space for coefficients, because you're going to have to balance these things, right? So you always need a little bit of space that you can write your coefficient in, okay? Or write in pencil, because you're going to be fixing things a lot. All right, so what's hydrogen gas's formula? Yeah, it's H2. Remember the diatomic gases? Hydrogen was a diatomic gas, wasn't it? So this one's H2. You got it. Got it. And so this is then going to yield. And what are we going to get for products?
Solid iron and water.
Got it.
It's just Fe.
Yep, Fe. And then don't forget the solid. Okay. And then plus H2O. That's perfect. And then what's the phase for H2O? Yeah, you're actually right to be a little confused, because this problem actually doesn't tell you.
That's L.
But L is logical for this. Yeah.
Okay.
It doesn't actually have to be L, by the way. In this case, it's going to end up being L. But, for example, if we were like high temperature conditions from this reaction, it could be water vapor coming off, steam. Okay, and so now we're going to go ahead and balance this up. What you always want to do is start with the stuff that's more complex. Okay? Start with the hard stuff first. Okay? Okay, so we see here that our Fe3O4, well, we actually need 4 oxygens, don't we?
Yeah.
Yeah. So Fe, we can take care of real easy. We can just put 3 in front this side, and we're done with that one, aren't we? But oxygens, we need 4 of those. 4 in front of H2O. That gives us equal numbers of oxygens.
That wouldn't make the H.
Exactly. That's why we do the hard stuff first, the complex stuff. Because, yeah, we now have 8 hydrogens, don't we? yeah, we need to get more hydrogens on the other side, don't we? Okay. And so we put a 4 here, and that'll bring us to 8 hydrogens on that side. In front of the H2.
Because it's creating water, H2O,
Yeah.
you have to add more of the hydrogen to it.
Yeah.
On the original side to
The
balance it out.
original side, okay.
Yep. You can change both sides.
Jeez, that's a hard one.
Yeah, it's just an equation. So just like an equation where you can multiply both sides, you can multiply both sides in this.
And then O just sticks.
And O is then 4 on both sides. Yeah. We didn't have to put any number in the F3O4 here because that one was already more than everything else, right? Okay, and so that right there is our balanced equation. Here it is in nice typeset, in case you don't like my writing. All right. Anybody have any questions so far? Okay. Okay, just remember you're balancing both sides, the number of hydrogens, oxygens, irons, each of the different elements, right? Okay, so this right here is actually an example of a reaction. Specifically, this one is going to have polyatomic ions. When we're dealing with polyatomic ions, we can actually deal with them as a set. So we can just take them as a single set that we'll move around and deal with as a set. Okay? Or another way of saying that is that you can act like they're a variable. Okay. And so this one right here, we're going to balance the following chemical equation. And so here we see we have a PO4 here, one of them, right? And over here we have 2 of them, don't we? Okay. So to get that to be equal, we're going to have to take and put a 2 in front of that N3PO4, aren't we?
In front of all that or in front of the PO?
The whole thing. Because that's one chemical compound.
Okay.
If you had tried to put a 2 in between that, it wouldn't be a chemical compound anymore. You couldn't break it apart. You gotta leave that as a single thing. Yeah. That'd be kind of like the old adage where, what is that, 2 parents are fighting over a child, and the king says, okay, then I'm just going to split them in half.
King Solomon.
King Solomon, yeah. Ridiculous, right? Doesn't work because half of a child is not a child at all, right? Yeah, if you literally split a child in half, they're no longer a child at all, right? They're dead.
I see on the one side it says NaPO, and then other side MgPO NaCl, but this one it says NaPO and MgCl. Instead of NaCl.
What are you talking about? This is different than this?
Wait, I was looking at the top. Okay, now I see that one's. It's like worked out. Okay, never mind.
No, they're the same thing. So the top and the bottom are the exact same. They're just colored. And what's happening
I was
is...
like looking at them like backwards, I guess.
Oh, okay, okay.
Okay.
Yeah, it's reactions occurring, and so we're swapping the anions between these two things.
Okay.
Okay?
Yeah, got it.
Okay. Yeah, if they weren't swapped, we wouldn't have had a reaction, actually.
Okay.
Okay. Okay, so to balance this again, we again have 3 mg's over here, and so we need to put 3 mg's over here, right? Okay, and our NAs now, we have 6 on the left side, the reactants, and so we need to put 6 over here. And now we make sure is everything even. Okay? Okay, we have 6 on the left, 6 on the right for NAs. For PO4s, we have 2 on the left, 2 on the right. So we're good for that. MGs, we have 3 on the left, we have 3 on the right. Those balance. Cl2s, we have 6 on the left and 6 on the right. So those are all balanced, aren't they? Okay. Anybody have any questions about that? you may have to practice. One of the things that you want to do is practice, okay? Because partially, if you're a little bit hesitant on the math part, I may have went a little fast on 2 times 3 is 6. Though, anyways. Okay, so we're going to try this together, and I'm going to have you balance a equation. Everybody ready to write down the equation so you can balance it? Okay, so the equation is Fe2O3, this is a solid, plus, and then it's carbon solid. This is going to yield Fe solid plus CO2 gas. And you have to balance that. Okay, go ahead and work on balancing it. I'm going to get the get ready part here. Do you guys remember where I talked about cross multiplication before? This is another place where cross multiplication becomes in handy. If you have a 2 and a 3, what's the easiest way to get those to equal each other?
6.
Exactly. Yeah, 2 times 3, 6. Yeah, it's the exact same thing we just did, isn't it? All right.
We're putting this one in.
Yep. I'll give you guys different options for the numbers that would go in. And you have to figure out which one it is. Oh, yeah, okay. You put it into the Q&A?
No, I like
Oh, no. Yeah. That's the easiest way to do it for you.
yeah.
And then, yeah, it'll just be the...
Whatever, blank, 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 blank.
Exactly. Yeah. Yeah, I still got some things to work out. This problem I needed to lengthen the amount of time to put it in. Okay, I'm going to flash this a few times up, just in case anybody misunderstood or anything was wrong with it. So this is the first time I'm going to flash it up there. Okay. I'll go back to it so you can answer in just a bit. Okay. Everybody got their answer in their head? Ready? Set.
Do I
Go.
need to re-answer it?
No, you're good. Yeah. See, yeah, it already has 11 out of...
Oh, it does.
Yeah.
Okay, I didn't see that in the top right.
Yeah.
Yeah, that definitely having to figure out match set. Okay.
Yeah, this one probably shouldn't have been timed. Yeah. But... yeah. Okay, so this answer right here. And so this one I'm actually going to have to go through a bit, and we're going to have to work this out a little bit. Okay, so the Fe2O3 going to reacting with carbon, right? And we're producing Fe and then CO2. Okay, so the first thing we always have to do is hit the stuff that's hard first. Okay? The stuff that has multiple things in it that we're going to have to balance. Because the stuff that only has one species, you just put a number in, you're done, right?
Yeah.
Yeah, you don't have to rebalance anything. Okay, so we have 2 Fe's, but on the other side we have Fe, so we don't have to worry about that. So yeah, that one's easy to deal with. We have 3 oxygens on the left side, and on the right side that's only with CO2, isn't it? And so when we balance the oxygens, that's going to be complex. Okay? Okay, so how do you balance 3 oxygens so it's equal to 2 oxygens?
Cross multiply 3 times 2.
Yeah, you do what would be called normally cross multiplication. 3 times 2 equals 6. That's what the multiple people had been saying, and yeah, got a really fast answer to it. And so that's going to give you 6 overall that you're trying to balance for both sides. So what we do is we put a 2 as our first blank. So 2 in front of the Fe2O3, which would give us 6 oxygens. And then we're going to put a 3 in front of the CO2, which is our last blank. Now, I will point out that as soon as you understand that and recognize this, that it's going to begin with 2, end with 3, you actually are down to only 2 options in this. So if you were time pressed, you could answer it right there, though it's not going to take us much longer to do it. Okay, so the 2 in front of the Fe2O3, that means there's 4 irons on the left side. And if we go ahead and try to equal out those irons, that means the number in front of Fe on the product side has to be 4, doesn't it? Okay, and so for the number of carbons, we had put a 3 in front of CO2. That means on the reactant side, we have to put a 3 in front of the C. So we have 3 carbons on both sides. Okay. All right, so we're going to try another question. Okay, this next question is going to be aluminum plus FeO yields, oops, well, shit. Ran out of time. Yeah, there you go. There you go. Hey. Yeah, I accidentally ran out of time when I was trying to talk about it. Yeah, so that one did not work out well for me. Yeah, I'm going to have to go through and take out the timers on these. Yeah. Anyways, let's go ahead and hit the next one. Al solid plus H2SO4 aqueous.
H2SO4.
You got it. Al solid plus H2SO4 aqueous. This is then going to yield Al2SO4, and then the SO4 has parentheses around it, and then that's going to be followed by a 3. Okay, everybody ready to see what that looks like? Like that. H2SO4 with parentheses around it.
And then add the H2 at the end.
Al2SO4. The SO4 is in parentheses, and then it has a 3. Okay? Then this is plus H2. All right. So, what are we going to do for the Al? There's one on one. Going to put 2. Okay, that makes sense. What are we going to do for the SO4?
So SO4, there's 12.
Put a 3. That makes sense. Okay. And then how about the on the right side, the products? Do we have to do anything with the Al2, SO4, 3? Nope. No. How about the H2? Do we have to do anything with that? We do. We do. We had to put a 3 in front of the H2SO4, didn't we? And so that's going to give us 6 hydrogens. So to make that equal on the products, we have to put a what in front of the H2? 3, you got it. Okay.
Al plus 3 H2SO4 equals Al2 parentheses SO4 3 plus 3 H2.
Got it. Okay, ready? Very ready to answer it. Ready, set, go. Oh, wow. Apparently my internet's really slow. Okay. And so, yeah, there's a 2 in front of the AL, a 3 in front of the H2SO4, a 1 in front of the AL2SO4 3, and then there's a 3 in front of the H2. Okay, so let's go ahead and talk about some types of chemical reactions. Anybody aware of what type of chemical reaction that is?
That's combustion.
That's combustion, yeah, or
Is heat.
burning, right? It's giving off heat. It's burning in the presence of oxygen, called combustion. All right, so these are the types of chemical reactions. We have combination reactions, decomposition reactions, single replacement reactions, double replacement reactions, and then the one that everybody loves, combustion reactions. So in a combination reaction, we're going to have 2 or more elements from one product. Simple compounds will combine to form one product. So we have simple things, they combine to form something more complex. Okay? That's why they're called combination reactions. Literally, we are combining things, aren't we? Okay, and so these are some examples of combination reactions. Here we actually have magnesium reacting with oxygen. This is why all the magnesium ribbons are typically dull, by the way. But this is actually going to be at burning. This gives off tremendously bright light, which you can't really tell from this. Anybody ever heard of a magnesium flare? Or flashbang grenades, the old ones? Yeah, those are usually magnesium powder grenades. Yeah. And that's right there is going to give us magnesium oxide, which is that snake-looking thing right there. Okay. Decomposition reaction. A decomposition reaction is going to take one substance. It's going to split it into 2 similar substances that are going to be less complex. Literally, we are decomposing from something more complex to something less complex. Notice it's the opposite of the combination reaction. Okay, so let's take a decomposition reaction. Here we have HGO, mercury oxide, and this is going to give us mercury and oxygen. And so that right there is a decomposition reaction. Taking a compound, splitting it into elements. Okay.
Is that an S next to the O? I can't see.
Solid? Yeah. Yeah, it was a solid. Okay, and so a single replacement reaction is going to take one element. It takes place of a different element in another reaction. We don't really get more complex. We don't really get less complex. We're just going to replace one element with another. This right here is an example of it. In this case right here, we're actually taking zinc, reacting with HCl. We're getting hydrogen and zinc chloride. This is also what's typically used for things like plating. Have you guys ever heard of like nickel plated or platinum plated? Yeah. So this is the type of reaction you typically use for that. In fact, right here you can actually see copper plated. That's what that would be. Okay, and so the next one, this is a double replacement reaction. We're going to have a positive ion in the reaction. It's going to switch places. And so right here you can see the silver was with the nitrate. Now it's with the chloride. Everybody said okay? Here we have NaCl, which is table salt. This is going to give us sodium nitrate over here. Okay. Notice that was that reaction we looked at before, where we had swapped the cations between the two. That's a double replacement reaction. This is an example of a double replacement reaction. Very, very common when we're mixing 2 liquids and we're forming a precipitate. We're actually going to do that in lab this week with a double replacement reaction, and it'll help us make chalk for use on sidewalks. Okay. Combustion reaction. Everybody loves combustion reactions. Combustion reactions, not to be confused with the combination or decomposition reactions, are very specifically going to be reactions where we take compounds, burn them in oxygen gas, and form carbon dioxide and water. Notice very specific reaction, very common reaction used a lot in our lives, right? So one of the things that's produced by combustion reactions is lots of heat and energy, right? Okay. By the way, when you look at a tailpipe, if it's functioning properly, what should come out of a tailpipe of a car? Yeah, carbon dioxide and water, right? It shouldn't have carbon monoxide in any significant amounts, shouldn't have black smoke. That means it's not functioning properly. If you look at a car on a cold winter day, what's coming out of the tailpipe that makes it look white? Yeah, it's water. Yeah, the water's freezing when it's hitting the cold air. And so you're just seeing little clouds, essentially, little contrails that are coming out of the car. Yeah. When people take pictures of smokestacks and they're burning, typically not coal. Coal burns very dirty. But like a natural gas plant, what's coming out of the smokestacks? Water. Those white clouds coming out of smokestacks, they're always being used for photos of pollution. Are kind of amusing, aren't they? Okay. So this right here is incomplete combustion. And so normally if you do a complete combustion reaction where you can actually burn everything properly, you're going to get CO2 and water. And CO2 is about as benign to you as it can get without it being nitrogen, essentially. Okay? However, if you do a combustion reaction and you do not have enough oxygen to fully do the reaction, some of what's going to come out is going to be carbon monoxide. Carbon monoxide is poisonous to you. In a typical car, this is why you have a catalytic converter. Does anybody know how much the catalytic converter costs?
$700.
Yeah, about $700, yeah. You can resell it by stealing it for people from like $400 something.
They just
Yeah.
put it off.
They do. And it's very, very expensive because the metal catalyst inside is actually quite expensive. Okay? And so if you have like an oven in your house that uses gas, or you have a water heater in your house that uses gas, guess what they do not usually have? Catalytic converters. And so they can build up carbon monoxide in your house, and they have killed people. There's a few thousand people worldwide that gets killed by this every year. Okay? Very common in places like China, by the way, because they don't put detectors and don't have laws that they have to have proper ventilation, etc. Okay? But anyways, so this is actually carbon monoxide. It'll bind to your blood vessels. It can be produced anytime you do a combustion reaction. You can produce carbon monoxide, okay? And it's just the incomplete burning of the carbon. It's a colorless, odorless, poisonous gas. It actually attaches to the hemoglobin molecule when you inhale. It's going to reduce the amount of oxygen gas that can actually reach your cells, because then your blood can't carry as much oxygen anymore. It's going to cause a person to experience a reduce in exercise capability, visual perception, manual dexterity. The most important part of this, the thing that makes it really dangerous, is that typically people don't know they're being poisoned by it until they get dizzy. By the time you've gotten dizzy, your ability to think has been impaired, and your ability to move around has been impaired. And so what ends up happening is they start feeling lethargic, they can't think properly, and they just sort of stay there and die. Yeah. And so it's actually quite dangerous. There's actually been cases of entire towns getting wiped out by carbon monoxide poisoning, usually due to volcanic releases. Yeah. Okay, anyways, this is actually the hemoglobin bound to carbon monoxide. That's what you would write it as. 10% a person may experience shortness of breath, mild headaches, and drowsiness. 30% a person may experience more severe symptoms. This will include dizziness, mental confusion, severe headaches, and nausea. 50% is a person would become unconscious and die if not treated immediately with oxygen. This is one of the problems with carbon monoxide. Carbon dioxide doesn't bind to your blood. And so if you have too much carbon dioxide, you're just not getting enough oxygen. That's the only real issue. And And so as long as you survive the 5-10 minutes of being unconscious and air starts coming back into you, you're fine. Carbon monoxide, on the other hand, you actually have to have it released from the hemoglobin. And so you have to greatly increase the amount of oxygen that person's experiencing, and quickly. Okay? And so this actually needs treatment. So if you have a burst of carbon monoxide, people are usually all unconscious, and there's not really anything that can get done. Yeah. And so they're very actually dangerous events. Yeah, anyways. You can look that up sometime if you're curious. It's actually quite brutal. Yeah. So these are a summary of the reaction types. Here we have the combustion, decomposition, single replacement, double replacement, and combustion. Let's go ahead and identify the reactions as combination, decomposition, combustion, single replacement, or double replacement. Okay, so right here we have this first one. What is that? A single replacement. You got it. One of the elements is replacing another, isn't it?
Which one of those?
Aluminum is replacing hydrogen. And so over here we have the aluminum combined to it, and that one has the hydrogen free now.
Okay.
Okay.
Yeah.
Okay, how about this next one right here? Okay, so the big one you want to look at here is we have a swap, don't we?
Yeah.
Yeah, and so that's double replacement. You got it. Okay, how about that one? That makes sense. Very good. How about this one? That's a combustion, right? We have CO2 reacting, and oxygen reacting with carbon, and it's producing CO2 and water. This right here, by the way, N2O2, giving you NO. That's an example of a combination reaction, right? Okay. Exactly. We have elements, they're combining something, a compound. Okay. Okay, let's go ahead and go on to the next one. What's this first one? Combination, isn't it? How about the B? Single replacement, very good. How about this one? Combustion, fantastic. How about that one? Double replacement, very good. Okay, okay. Did you change your mind? Or? Okay, yeah, you got it. Decomposition. Okay. Okay, so this is actually another example right here of a reaction where we have rust. This is specifically a more specific term for this one is what's called oxidation reduction reaction. And so rust is going to form when the air reacts with the iron. Electrons are going to be transferred from one substance, the iron, to another substance, which is the oxygen. Okay? So the oxidation reduction reaction is going to provide us energy from food. It's what typically provides the electrical energy that we're going to store. It's going to occur when we have an iron, for example, rusting. Okay, that's the oxidation that typically occurs. And you've probably actually heard the term of half of that reaction before, oxidation. You may never have heard of reduction, though. Yeah. So, in the oxidation reduction reaction, oxidation and reduction always happen as pairs. And that's because they're always going to be where one loses an electron. If something loses an electron, that means something had to have gained an electron, right? And so the oxidation reductions are always pairs. It is always a yin-yang. It is always together, okay? If there's an oxidation, there had to have been a reduction, right? If there's a reduction, there had to have been an oxidation. Always has to happen as pairs. Oxidation is going to be the loss of an electron. Reduction is going to be the gain of electrons. Remember, electrons are negative, and so if you gain electrons, you are being reduced, aren't you? You're taking on negative charges. Okay? Oxidation, by the way, the loss of electrons, oxidation is actually named after oxygen, because oxygen is the most common oxidizing agent. It's the thing that oxidizes stuff the most often. Okay? This right here is actually an example of an oxidation reduction reaction. Again, what was her color supposed to be?
Isn't it like copper?
Yeah, it's a brass actually, but yeah.
Yeah, brass.
Yeah, a little bit of copper cladding. She was actually originally gold. Yeah, gold color. Like beautiful, shiny gold. Yeah. They actually wanted to restore her about a decade or so ago. And I guess it would be about 15 years now. But the locals protested and didn't want the restoration done. They wanted the statue kept green.
Just because that's how it's been known for so long.
Yeah, it's
Yeah.
become iconic, right?
Yeah.
Yeah. Though the funny part is, in reality, this is oxidation. It is somewhat protecting the metal under. And so they would have had to put some sort of coating or something on it to keep it that way.
Yeah, that would have been very expensive.
No, the amount of restoration they do on this thing compared to the amount of money they already have to spend is that'd been minuscule.
Well, then, like, they can't just replace it and tell them, oh well, and put the coating on it so it just doesn't keep on
Yeah.
getting worse.
They could have. They
That's stupid.
did
I think it would
not want it. Yeah, and there's all sorts of problems. Like there's parts of the statue that are not structurally sound anymore. And so, and they cannot, it's become a whole thing in New York. Yeah, you can get into it sometime if you're interested. Okay, so this reaction is actually the copper reacting with oxygen. And that's what's forming the copper oxide, which is that green color stuff here, okay? And that's an oxidation reduction reaction. Specifically, the copper is losing electrons, being oxidized, and the oxygen is gaining electrons, being reduced. Okay? This one right here is actually a bit of zinc getting thrown in there. And so if you throw a bit of zinc in here, what you'll actually see is this will then have a reaction where the zinc will get oxidized, the copper will get reduced, and come back out. Anybody ever heard of galvanic protection? No? It's how you keep pipes from rusting. You put a little piece of magnesium connected to it, and that gets oxidized instead of the pipes. Okay? This would be a very, very similar thing. You can actually do galvanic protection of copper with zinc. Okay? Let's identify each of the following as oxidation or reduction. So is this an oxidation or reduction? So oxidation is where? Yep, oxidation, because we're losing the electrons, right? Okay, this one right here. It's a reduction, because we gained an electron, didn't we? Okay, how about this one? Are we gaining or losing electrons? There's an easy hint to give you. We're gaining electrons, aren't we? Because it's on the reactant side that the electrons are out. Okay, and so that means it's a reduction. Okay, the other way you can look at it is it's going from a 0 charge here to a -1 charge here. And so it got more negative, right? It was reduced. Okay. So in the light-sensitive sunglasses, like my sunglasses right here, you may see them turn colors sometimes from the light. The UV light is going to initiate an oxidation reduction reaction. And so in the glasses, there's silver ions and there's chloride ions. When the UV light initiates a reaction, it's actually going to cause an oxidation reduction reaction. And so here the silver is actually going to get reduced. The chloride, on the other hand, is going to end up being oxidized. Okay? So which reactant is oxidized? Which reactant is reduced? And this is going to be a quiz. Everybody ready? Got something in your head? Ready, set, go. So which one's oxidized, which one's reduced, or are they both oxidized, both reduced, none? Doesn't happen? Okay. And the chloride is oxidized. The silver is actually the one that's reduced. Okay. All right. So again, when we were looking at this, the silver went more negative, didn't it? The chloride went more positive, didn't it? Okay. Okay. So we got 5 more minutes or so. We're not going to actually be able to finish up the chapter this time. So that means the exam is going to get pushed to Tuesday, okay? I'm going to push the exam to Tuesday. We can't push it anymore. So it doesn't matter if we finish or not. That's it, okay?
Made my day.
Oh my God! Like,
Alright, now I can just go on, Dr. Mason.
Wow.
I'm done for the day.
Lots of happiness.
yes.
Okay.
Oh my God.
Okay, so we're going to put in 4 more minutes. Let's go ahead and go this last bit. So right here we again have an oxidation reduction. Has anybody ever heard of FAD or FADH?
Yes.
Have you guys heard of NAD?
Yes. Oh, that's the molecule in like photosynthesis, right?
Yeah. Yeah.
NAD plus and all that.
Yeah. Yeah. And so NAD plus and FAD, these are the 2 major oxidation reduction agents in your body.
Oh my God,
Okay.
I just joined biology.
Well, then that was
I know.
We're going
Bam.
over FAD in biology.
That's what, yeah, we're doing that.
Yep, there you go.
With authors.
And so the 2H in a biological molecule are going to get transferred to what's called a coenzyme, FAD. This right here is an oxidation of that biological molecule. FAD is reduced and is now carrying that reduction capacity.
Because of the hydrogen.
Exactly. And so you would then move it, say, into an energy production pathway that you could get ATP or something from. And you would harvest those hydrogens off to build up energy to make the ATP. Okay? Or you could directly use the FADH2 to reduce something. Okay. So in many biochemical oxidation reduction reactions, the transfer of the hydrogen atoms was going to be necessary for the production of energy. The body is going to metabolize things like methyl alcohol, which is a poisonous substance. And here we are actually seeing methyl alcohol being oxidized in this case. Now, in a biological system, there's a little trick we can play. We don't necessarily need to keep track of the electrons in biology. Typically, it's good enough to keep track of the oxygens and hydrogens. Okay? So, for example, in this case right here, we've lost hydrogens, and so we're being oxidized. Gaining hydrogens would be being reduced. Okay? Here, we're going from formaldehyde to formic acid. Anybody know what formic acid is? You probably heard of formaldehyde before, right? Okay, so formic acid is actually the stuff that, like, the Asian beetles, ladybugs, spit at you, and it feels like they're getting bitten. Anybody been bitten by an Asian? Yeah, it stinks. That's why when you smash them up, it smells like fresh cut grass, but really bad. Yeah. Yeah. Also, what the small ants spit at you. It actually tans your flesh. This is why drinking methanol is really bad. It actually tans your flesh inside your body.
Considering that flesh is meant to be soft and squishy,
Yeah, it's a
rough and leathery.
big problem. Okay, so this is gaining oxygen. Gaining an oxygen means it's being oxidized, right? Okay. And then right here we have formic acid. Eventually this formic acid is going to be produced into CO2, which is how you get rid of it.
Yeah,
And that is again being oxidized. Everybody say okay?
because you're adding the oxygen. Okay,
Exactly. We're losing hydrogens, gaining oxygen, aren't we?
gotcha.
Yeah.
Makes sense.
And so you're going to see that 2 of the intermediate products of methyl alcohol are actually toxic. This is actually the big problem with methyl alcohol and why it's so toxic. The ethanol, on the other hand, is a lot less toxic because it produces much less toxic intermediates. Okay? Anybody know what ethanol versus methanol is? Ethanol is the alcohol people drink. Methanol is the wood alcohol. The stuff you put into like Formula One racing cars. Okay. You all have a great day. I'll see you Thursday.